Okay, thanks everyone for hosting me. I'm really excited to be here. And I mean, I hope the excitement doesn't affect my presentation skills and I can still deliver what I want to say. I'm Donato and I'm from Rome. I will be talking about model merging today. Now, get comfortable because we are going to start with some cinema. Now, I'm pretty sure everybody, I mean, not everybody, but most of you remembers this scene. So it's the one where in the first Matrix movie, Neo is basically getting updated with a new skill, in this case Kung Fu, because he has to go and fight Agent Smith. Now, how cool is this idea? Not the one of fighting AI with your hands like Neo does, but the fact of having some kind of knowledge transfer which is instant. So it doesn't take hours or days or months, but you can just have a new skill within seconds or minutes at most. Well, it would be cool, for instance, if for humans we could share knowledge, and let's say that we have Alice who knows geometry and Bob who is a biologist. It would be cool if we could do some kind of human algebra and get Clara, which is a structural biologist. Now, too bad, but we just can't do it. Like our brains are not wired to do that. But it turns out to be real, to be working for models. And this is the way I like to think about model merging. Now, enough with the sci-fi. Let's try to see why we have two settings in the first place. So in the first one, can you still hear me? Because I have some kind of feedback. Can you hear me?
Yep, we can
Okay,
hear
cool.
it.
Yeah, nice. So in the first one, we actually start with different seeds. So we got the same model architecture, let's say a ResNet, and you train it from scratch on the same task from different seeds. What you obtain are two different trained models, which you can try to merge, maybe with a simple mean, to obtain a single one. Now, why would you do that? Well, maybe this model is going to be more robust, or maybe you are doing pre-training of a large foundation model, for instance, and you are doing some kind of Polyet averaging, which is something that makes the training smoother. The second setting instead is the one in which basically you start from the same foundation model, let's say this is your Clip or Mistral or whatever model, and you fine-tune it on different tasks. So you obtain, for instance, a model fine-tuned on task T1 and one fine-tuned on task T2. And then you want to merge these ones to obtain a single model that can do the two tasks at once, or maybe the n tasks at once. So you see that we have different objectives here and also different challenges, as we will see. So I will start with the first setting. And to do that, we have to introduce some terminology. So first of all, we will talk about modes. What is a mode? So a mode is the set of weights of a model at convergence. So let's say that here I have two different random seeds and I got two different training trajectories, and one ends up in this basin and this other one ends up in this other basin. Now, each one defines its own basin, as you can imagine from the plot, and these ones were once believed to be isolated. So basically, people believed that you couldn't go from one to the other without having an increase in the loss. So when I say that two modes are connected, I mean that you can just walk from one to the other and your loss will not increase. Then somebody came up and said, look, but maybe these modes can actually be connected with narrow tunnels of low loss. So you can still keep the loss low while walking from one to the other, but these are like very narrow tunnels, maybe highly nonlinear tunnels. Then later on, people started believing that actually these modes live in the same low loss manifold. So there is a way to go from one to the other, and it is not that narrow actually. It's like a huge valley beneath many mountains, but it is not narrow, it's not a canyon. Now, if you got two modes, there are different ways to connect these ones. You can use Bezier curves, polynomial chains, but we care the most when the path is actually linear. And why? Well, because if the path is linear, then it means that if I take the mean of these two modes, then it will be a good model. It will be a model with low loss, and therefore a model I can use. So in this case, merging becomes just a simple mean. Now we will say that when two modes are linearly connected, we will say that they share the same convex basin. Okay, how can you check whether two modes are connected? Well, we need some tools. The first one is the loss barrier, which basically tries to measure how linearly connected two modes are. And how does it work? Well, it looks fancy, but actually you're just seeing, you're just measuring. When walking on the line from theta A to theta B, these are the two modes we care about. So you just draw a line between them, and you walk on this line, and you see if your loss is actually increasing. So if it does by a lot, like if you always expect it to increase a bit, but if it increases by a lot, it means they are in two different basins. While if it stays more or less flat, or it just increases a bit, then you can say that these ones actually live in the same basin. So the barrier is just this quantity here. Now, if we know how to bring two modes in a single basin, then we got a nice recipe, which is just, yeah, take them in. Because if I know that they are linearly connected, I can just take them in, and the model that I get will be a good model, as we said. Okay, so now we just need a way to get modes to be in a single basin. Okay, now we just need some more intuition here, some more ingredients. So this is very important, not just for model merging, but in general. You always need to remember that neurons have these permutation symmetries, and you cannot really like take the mean of different neural networks without accounting for these ones. So let's see what I mean by that. So let's say that I have some linear, okay, at some layer, and let's say that I want to shuffle the rows of this linear. Okay, so maybe the first row gets to be the second, and vice versa. Now, what happens to the output? Well, the output will be basically the shuffled version of the output we had before before this permutation. By the way, when I shuffle, we just mean that we multiply by permutation matrix from the left. It means you are shuffling the rows of the matrix. So these two outputs are different. I mean, if you look at them, they are different vectors, right? But what happens if I now also permute the columns of the next layer by the transpose of P, which is the inverse of P because P is a permutation and therefore it's an orthogonal matrix. So again, we just took a network and we modified the two layers by shuffling some rows and shuffling some columns of two different layers. Now, if you do that and you compute the output of the next layer, you get something like this one. So you are going to have the new layer, which is just the column permuted layer, times the output from the previous one. We know which what this is because we have it here. And you see that basically what happens is that the permutations end up canceling each other out. So you see they compose to the identity because, as I was saying, a permutation is an orthogonal matrix, and therefore you can just compute the inverse by the transpose. So we have here two different networks because if you look at the weights, they're different. If you compute the L2 between these two network weights, they're different, which end up in the very same output, like in the very same function. So we will say that these ones are functionally equivalent. Now, I know you might be asking, yeah, but what about the nonlinearity, right? Well, it turns out that we can, it still works, like this reasoning that we are doing still works because the nonlinearity is element-wise, and therefore it commutes with the permutation. Because if you apply something element-wise to the single elements of a row, and then you shuffle the row, or you first shuffle the row and then apply the element-wise operation, it's the same output, right? So think about it for a moment. What am I saying here? Here we're saying that there is a huge amount of neural networks because you know that permutations are quite many that are actually functionally equivalent. And whenever you initialize the new network, you don't get to choose which neuron permutation, which configuration of the neurons you are getting. You just get one at random. It depends on the data, on whatever the stochastic factors you got in your training. So this has led people to believe that maybe if we take into account these permutation symmetries, all the modes will end up sharing one single basin. So if you take into account the permutations of a model and you, let's say you solve for these ones so that they match the permutation of another one, you can basically teleport this one into the basin of the other. This is the reason behind V3 basin. It was very popular like 2 or 3 years ago. So you just say, look, okay, I know that maybe if I rule out the permutations, they share a single basin, so I just solve for the permutations. How can you solve for the permutation of the neurons? Well, you don't even need data to do that, because you can compute just the similarity between the neurons themselves. Like these are vectors, right? So you're just saying, look, I'm going to find the permutation, which after I apply it, will have the corresponding neurons as similar as possible. Now, you know, there is always like all the interesting problems, this actually NP hard. So you cannot really solve for this one, but you can try to approximate this one, and maybe it will still work out. And it does in practice very often. Okay, now, the first work of mine that I want to talk about today is basically asking one simple question, which is, okay, but what happens if I have 3 models, let's say A, B, and C? So until now, we've seen pairwise methods. So basically, they only work if you got 2 models. But what do you do if you have 3 or 4 or 5 or whatever? Well, you could still try to match all of the possible pairs. It's something you can do. So you are going to find, in this case, 3 permutations, right? One from A to B, B to C, and C to A. The thing is, if you do this and you try, let's say that now I want to go from A to B to C, each time using a permutation of the neurons, and then I end up back to A. You see that here, basically, each time you accumulate some error, because you are not getting B when you permute A. You're getting something which is close to B. It's actually the best approximation of A in the basin of B. So what happens is that if you look at the loss barrier or the accuracy barrier, which is basically almost the same upside down, you see that if I check A and A after I did this cycle of compositions, so I went to B and C and then I came back to A, you end up in a different basin. So you accumulate so much error in the path that you actually end up in a totally different basin. So this means we are lacking cycle consistency of the maps, which can also be stated in this way. You're just saying that the composition of these permutations doesn't compose, like, is not equal to the identity. Okay, now, this is an image for structure from motion, task they do in graphics. And basically here the task is to, so in this case, what we are trying to see here is that if you want to, for instance, match 2 different images, and you've got access to a common 3D model in this case, it's easy to do that because you can just match this one onto the 3D model, match this one onto the 3D model, and then maybe I just need to go to the 3D model using this one as a hub and go back from the 3D model to the target image we want to match. So here we're saying if you have a universe, a common space you can use, then matching many objects becomes simpler because basically you can use this one as a hub. And this way you also have cycle consistency because each time you pass through the universe, you don't accumulate error. So how can we do that with model merging? Well, we just start from the same equation we've seen before. So we are just trying to find the permutation that maximizes the similarity of this of the neurons of the 2 layers of the 2 models. And then we consider a simple factorization of each pairwise map into a map that brings you to the universe and one that takes you back from the universe to the target model. So it looks like this. If I want to go from A to B, I take a map to the universe and one that takes me back from the universe to B. Now, this is quite easy to see, but it can be shown that in this way, you are guaranteed to be serial consistent, so you don't accumulate error like we did before. All right, we have also some benefits of using this formulation. The first one is that basically in D3 basin, you usually randomly select a layer, you solve the optimization for that layer, and then you go to another random layer. That's because, as I was saying, that problem we were looking at is NP-hard, so you need to have some kind of approximation. In the case of D3 basin, you're just approximating layer-wise. Here, instead, we solve it with Frank Wolf, which allows us to solve for the linear approximation of the problem. And in this case, we are not fixing a layer, but instead we jointly optimize for all the layers together. So in this case, we don't have any variance arising from different layer orders, which is something that you instead have in the tree basin. Okay, here you can see what happens after you map to the universe, these three basins, and before mapping. So you see that originally they were in different isolated basins. After we map them, you can go from anyone to anyone else, and you still stay in the same basin. So we basically obtain what we wanted. So this gives us a simple way to do the merging. You just take the mean here. You just take the average of these ones, and you're fine. Okay, this was the first setting. This one, it's a bit shorter than the second one, so I went. We still have a lot to cover, so I went a bit fast. By the way, if you have any question, and I mean, I think you usually do them like after the talk, but
Yeah,
yeah.
we can do them at the end. Yeah.
All right,
Yeah.
cool, nice. Okay, so let's now start the second setting instead. Okay, so you might remember from like 10 minutes ago that the second setting means that basically we start from the same foundational model, let's say Clip or Mistral, and we got different fine tunings for different tasks. Now, we usually don't want to use data for these fine tunings because you might just have to download them from Hugging Face. Maybe you don't want to do the fine tuning yourself. Maybe you just go on Hugging Face, download Cypher, MNIST, or whatever, and then you want to obtain one single model with the same number of parameters and no extra inference overhead that can do all the tasks at once. You can do that for vision or for language. Okay, so one very popular approach for this one is task arithmetic, and it works like this one. So basically, you say, okay, I'm gonna start from my base model, let's say Clip, and I fine tune this one on a task, let's say T1, or maybe I just download the fine tune checkpoints from Hugging Face. Then what I do, I compute the difference between the fine tune model and the base, and I call this one a task vector. Now, if you do this for a couple tasks or n tasks, you obtain n different task vectors. In this case, true, right? It turns out that if you add these ones together, so if you add the task vectors together, you obtain one single vector that basically, when integrated onto the base, will give you multitask capabilities. So in this case, the merging we wanted to achieve, the multitask model we wanted, can just be obtained by summing the task vectors onto the base. This is from iClear from a couple of years ago. So this gives us a very simple recipe for the second setting, which is, okay, I just compute the task vectors, I remove any kind of interference that may arise, and then I just aggregate these ones and back onto the model. But what do I mean with interference? Okay, so until now, when I said that we were adding and subtracting stuff, we were actually talking about vectors which are in the hundred of million dimension or maybe billion dimensional vectors. And we are just saying, okay, I'm going to flatten this one, and then I'm just going to consider this one to be any vector. Okay. So if I'm going to use Mistral 7 billion, I'm just saying, yeah, I'm going to add these very huge vectors together. Now, why are we ignoring the fact that these vectors are actually the weights or the difference in weights of a neural network. So maybe the coordinate at I don't know, uh, coordinate 700 maybe refers to the second neuron of some linear layer, for instance. So why do you want to waste that structure and consider all to be flat? So what we say instead is that we should actually keep the structure, the layer structure at least, and do all these operations at a layer level. So until now, this totally equivalent, right? The end result will be the same. Like either you do flattened or you keep the matrix structure. In the end, the result will be the same. But now that we have this structure, we can try to come up with some fancy way, some smarter way to aggregate and study stuff like task interference. So, for instance, the first thing that we do, well, after renaming this tau to delta, because now we're talking about matrices and not vectors, the first thing we try is to say, well, why don't we study the SVD of these delta matrices? So again, if this is a linear, this is going to be, let's say, a linear, I don't know, 100 times 100. This is going to be 100 times 100 matrix, where in each coordinate you got the difference between the fine-tuned and the pre-trained. Okay, so we got these delta matrices. Can we actually leverage this structure in some sense and see, for instance, if it is low rank? So I'm gonna be fast here, but if you don't know how SVD works, just ask me. So basically in SVD, you decompose any matrix as the product of two orthogonal matrices, which are called the left and the right singular vectors, times a diagonal matrix of singular values. Now, this can also be written in this way. So basically you got a summation of a number R, which is the rank of the matrix, of rank 1 components, which are obtained in this way. The outer product of the left singular vector, a right one, scaled by the corresponding singular value. Okay, so if we want to see the rank, usually what people do is to say, okay, I'm just going to keep maybe K of these rank 1 components and see what happens. So we are just taking a subset, like the most important rank 1 components of this matrix, and just throw away the rest. This is something that people do all the time. So if you do that, you see that basically with just 20% of the singular vectors, you obtain something like, I don't know, 99% of the total accuracy. So these deltas are actually extremely low rank. So whenever you see that something is low rank, you usually say, okay, then maybe the least important stuff is just noise, and I can just remove it. And if I do, in this case, before we aggregate these task vectors, I will end up with better results because it's kind of a more clean sum. This like a denoising step. Now, we tried that, and we actually lost like 2 accuracy points. So it wasn't the case. And so we were like, yeah, but why? I don't know. This just doesn't make sense to me. So we went and checked, okay, but what is the relation between singular vectors of different tasks? So we just computed the dot products between all the singular vectors for each task and those of another task. Let's say in this case, just 2 tasks. So you see here that at the diagonal, of course, you got just the singular vectors of one task times themselves, which is the identity matrix because these ones are orthonormal. But whenever you multiply singular vectors of different tasks, you end up with this kind of noisy heat map, which is telling us that these ones are not orthogonal at all, and there is quite a strong interplay between these ones, which is what we call interference in this case, which we call singular interference. Now, this is higher for more shallow layers and lower for deeper ones, probably due to shallow layers being more general and therefore having more interference in the first place, while more deeper ones probably are more task specific and therefore interfere less. But that's more or less like a hand waving explanation. So given this this consideration, we came up with a very simple algorithm. So basically, let's say that I've got 2 different layer delta task matrices, this deltas here, for some layer here, maybe we are, I don't know, the third layer, some linear, for instance, and we compute the SVD for each one. Now, these ones, like if I just focus on the left singular vector, well, first of all, we want to compute a low rank approximation. Okay. Now, if I focus on these ones are already orthogonal one with the other, but they are not orthogonal with respect to those of different tasks. So what we do is we just orthogonalize these ones with respect to the ones from all the other tasks. Oops. How you can do that? Well, you can just concatenate these ones and then solve for permutation step, which is basically just giving you the closest orthogonal matrix in Frobenius norm. But it is not really important. What we need to remember is that you just need to orthogonalize these ones between different tasks. Then you can find different ways to do that. Okay, now if we do this orthogonalization step without the low rank approximation, we already get something like plus, I don't know, 5 accuracy points. But if you do this with the low rank approximation step, you end up with something which is like plus 15 points in accuracy, which was quite amazing and quite hard to believe at the time. Okay, so well, this more or less consistent on all the datasets that we tried. We tried up to 20. Here you just see a bunch. And also, this gives us a way to compress models. Now, what do I mean by that? Well, let's say, so first of all, what we've seen until now can basically be stated in this way. So we are just saying you can just sum the orthonormalized singular vectors, like rank 1 components resulting from the singular vector multiplication here, for the top k singular vectors of each task for all the tasks. Okay, now, if I knew what task I wanted to solve beforehand, so if I know that I'm just going to solve MNIST, then basically what you do, you just throw away the other singular vectors, like the ones from the other tasks, and you just end up with basically a low rank approximation of the deltas for that single task. So for instance, if I want to do cipher, I'm just keeping the singular vectors coming from its fine tuning. So if you do that, you end up with basically a compression algorithm, which is just taking the low rank approximation of the deltas. So here we're just saying in a fancy way that if I know the task, I'm just keeping those ones. Okay, if you do that, you see that you end up with something that's something like 99.5% of the accuracy that you will get with the fine-tuned, with something like, I don't know, 10% of the size. Okay, now, what usually happens when you need an oracle, like now, so here we're saying, yeah, if somebody came to me in my dreams and told me what task I would be solving. Well, in computer science, when you need an oracle, you go and build one. And these ones are usually called routers in the field. So what we say here is, look, what if I find a way to do the routing without requiring the data for that task? Because if you require the data, well, it's not really model merging. In this case, you usually assume that you just download your models from Hugging Face. But what if we don't need the data? Okay, so let's try this recipe. So we do 2 passes. In the first one, we feed our input to a model just to get the embedding of this one. Okay, so maybe the model we use may be a model we obtained by merging with the previous word we've seen, for instance, or maybe it's a base model. Then when you want to do the routing, you do the following. You say, look, I'm going to see, given my embedding Z for some layer L, I'm going to see to what subspace it is most similar. Like if I project this one onto the subspace of each task spanned by the singular vectors, the right singular vectors for that task, in which one my residual, my difference is minimal. So in which one my projection is less error prone in some sense, is less lossy. So you do this for all the tasks. You end up with a vector which is as long as number of tasks. These ones may resemble logits, and in fact they are. So you can just compute the softmax of these logits, and you obtain a probability distribution over the tasks. Now, you can also have a step where you say, okay, look, maybe I'm just going to keep the tasks which are above some threshold. That is just a way to have less tasks to merge. And then you can do the merging now after this routing step with only the tasks that are actually important for that input. So basically, we've got a routing step, which is similar to mixture of experts, but that allows us to reuse already fine-tuned experts. So this is why this kind of works is called mixture of experts merging or merging. So now that you have your new model, which is adaptive in a sense, now it is dependent on the input, you can just do a second pass with this new model you just merged, and you use this one to do the classification or whatever task you wanted to do in the first place. Okay, if you do this, well, you obtain very, very better results than the fixed merging methods. So routing actually helps. But to be fair, we do it in a more challenging setting. So we are not using the ground truth, like we are not using the classification head for the task as if we knew what the task was, but we're actually also routing on the task head, which is different from what model merging methods do. They usually assume that you know you are evaluating MNIST, so they just use the classification head for MNIST. Here instead we are also routing on the head, so it is a bit more challenging. All right, now, okay, this is the most surprising one. So bear with me because this experiment is very, very interesting and insightful, and I still didn't fully grasp why it happens, but it does. So, okay, we've seen that the right singular vectors, these right singular vectors here for the different tasks, this V, we've seen that they are very good for routing, so they're meaningful for the task. Now, and I mean, if you forgot about it already, like these ones are just the right singular vectors for the from the deltas for each task. So these ones, you're going to have a set of k right singular vectors for each task you are actually using. Now, what we do here is we say, look, can we try and interpret in some way, decode as text, as a caption, a set of captions, the right singular vectors of the deltas. So we used an algorithm which is basically used on images to get captions, usually, like to get an interpretation of image embeddings. And we used onto those right singular vectors, which are not data, they are not embeddings either, they're weights. So here we are trying to see if there is a mapping between weights and data, so weights and text, for instance. And if you do this for these 4 datasets, so we got CARS, DTD, MNIST, and Eurosat, and here the images, we don't use them. These are just for reference to show you what these datasets are about. So if we do that, and you try to decode these weights with a text that gives you a caption, we end up with something which is extremely relevant for the task. So for instance, for the CARS dataset, we got image of a car. For the DTD, which is this weird dataset of textures, we got close-up of a texture synthetic mesh. For MNIST, we got an image of the number 9. And for Eurosat, which is kind of satellite images, we got aerial view of an agricultural field. So they're very, very relevant for the task, which was really surprising to me, actually. Because here we're not even talking about weights. We're talking about the singular vectors of the weights, and not even the weights, but the differences of the weights. So I know it's confusing. It is to me still still today, but it actually happens. It is something that happens. And so here is another interesting fact is that basically, if you do this for a VTL14 for some clip model, and you do that for still for clip, but on a different vision transformer, you end up with very similar captions. So even if the architectures are actually different, which is kind of interesting and insightful. Now, just as I would say, as a safety check, we also try doing this one at some more shallow layers, which we don't believe to be that meaningful, to be that rich of semantic. So we did it for the third layer, and we got all irrelevant stuff like aerial view of a hamlet, or image with a penguin, or yeah, photo taken in Santorini when you are actually looking at MNIST. So this only holds for the more deeper layers which have more semantic. Otherwise, the first ones are not that good for the task. And indeed, these ones are the deeper ones are the ones we use for routing. Okay, now we are switching topic. Now we are talking about merging LLMs instead. Okay, so people do merge LLMs a lot. Like on the OpenLLM leaderboard, last time I checked, like 30% of these ones were the result of some merging. Now, if you use, for instance, task arithmetic, then you end up with something that looks like this one. So you want to obtain your multitask vector, you just compute some average or whatever, like some weighted sum of your task for the different of your vectors for the different tasks. Now, the community is lazy. Like usually people just say, okay, I'm going to take the mean, or I'm going to try some handcrafted values. But can you do better than that? Well, the answer is yes, and this is something that Sajana AI did like last year. I mean, the paper is from this year actually. So what they do, they say, look, why don't we use evolutionary optimization to find these hyperparameters, these lambdas here, so these interpolation coefficients. And how does it work? Well, basically you start with your two LLMs you want to merge, or three LLMs, or whatever. And let's say that we want to obtain a French mathematician model. So we start from a French LLM and a mathematician LLM. Now, you give you basically want to obtain their interpolation coefficients. So you start with a vector in which you got one for the first, and and another one hot vector for the second one. And then you compute all the interpolations between these ones. Now, these models will be your first population. Now you challenge these ones at a French plus mathematics skill tournament. You say, okay, I'm going to ask them a data set of questions of samples in French and of samples in maths. Now, let's say that you do this, and yeah, the first one is very good at French and very poor at maths, and the last one is the other way around, and then you got the in-between models. Now, at the end, you get some winner here. Let's say this guy right here won the tournament. This one will be the parent for the new generation of models. So you end up with another generation, another population of models, and you do this tournament again. You again compute the evaluation over these data sets, these task data sets, and you use this one as fitness for your evolutionary framework. So you do this a couple of times, you end up with your winner, which is our Fourier LLM, because it was a French mathematician. And maybe this is some kind of interpolation between the French LLM and the math LLM with some coefficients. Okay, now this is cool, but basically an evolutionary algorithm looks like the following. So you say, okay, I'm going to decide a number of iterations, and then for each iteration, for each model in the population, I'm going to evaluate this model on each of the data sets for each task. So now these ones are huge models, these ones are LLMs, and the data sets as well, they might be in the thousands or tens of thousands of samples. So each time, you see here, you got a double 4. Each time you want to compute the fitness, it takes hours to do that. So you get state-of-the-art results, you do, but it's very costly. And if you only have, I don't know, a consumer GPU like I do, like maybe you got your NVIDIA 4090, it's gonna take, well, quite a bit to do that. So yeah, you need a cluster to do this stuff. Instead, we propose an alternative which allows you to do it in just 1 day of a consumer GPU, and still allows you to get a very good accuracy approximation than the original one. Okay, how does this work? Well, there is this field which is called the item response theory, which basically tries to do the following. They say, look, I'm trying to evaluate maybe the intelligence quotient of some individual. I can't ask them like, I don't know, 2,000 questions. You can just maybe ask 20 because people will get bored and will not take the test otherwise. So the goal of this field is to be able to approximate some quantity for a whole data set given just a bunch of samples. So this is precisely what we want to do, because basically, if we can approximate the accuracy over the full evaluation dataset, which we use for the fitness computation, given just maybe 20 samples, then our merging pipeline, our evolutionary merging pipeline becomes way more efficient. Okay, so how does it work? Well, okay, just maybe ignore this part. Okay, now look at this stuff here. So if we know how to estimate, given 3 parameters, 2 for each sample and 1 for the model, which like the probability of the model of being right on that sample. So I have a function that given a sample I and a model M gives me the probability of the model being right on that one. I can just compute the mean of these probabilities over the full data set just by evaluating this function without actually running the evaluation for the model. And this gives me an approximation of the actual accuracy of the model. So if you have a way to estimate these parameters here, this gamma, alpha, and beta, then basically the evaluation is for free. You just evaluate this function over all the samples and you're fine. So you don't need to do the actual LLM evaluation. You don't need to generate anything. Okay, how does it work? Well, it is very simple, this kind of logistic model. Basically, you got a discrimination vector, which is dependent on the sample, which tells you what skills are needed for that sample. Then you've got a latent ability vector, which instead states what abilities the model, that particular model M, actually has. So you see that here, basically, you've got that the more they are aligned, so the more the skills needed for the samples are aligned to those that the model actually has, the higher this quantity will be. And then you also have a beta threshold, which is basically just the difficulty of the sample, because maybe you know that that sample is, I don't know, a French sample, but this doesn't tell you how difficult it is. Okay, so if you know how to compute these ones, as I was saying, you can just approximate the full accuracy, just given maybe, I don't know, 20 samples that you use to estimate these parameters. And this is what we do in this paper. Now, okay, so we allow in just 1 day to do very cool stuff. Like here, for instance, you were just transferring skills between different languages. For instance, if you want to transfer math skills from English to German, you see that here we got like the baselines, which are something like this, the German baseline. This is 2 math baselines. Then you got the merging baselines, which they don't do that well, actually. They even perform less than the actual math baseline. And if instead you do the via evolutionary merging, you get something like double what you will get from the baselines. But it works very well. And we tried for different languages, and it still applies. You can even do something even maybe more cool than that, which is, let's say that I've got 4 different models each one for its own language. So these ones, if you got Mistral, this is 7 billion, 7 billion, 7 billion, 7 billion. So you got four different models. What if I merge these ones together and I get one single model that actually outperforms all of these ones together in the tasks that we tried? So now you got even better results with just one single model, which is kind of impressive. Okay, we released a library to do so, so you can merge your own models, and it should be easy to implement.
Hey,
Yeah,
Donato,
yeah,
can you just wrap it up in 5 minutes?
yeah. We're done actually. Yeah,
Okay,
thank you.
cool.
Yeah, so basically, we even released a library very like a couple of weeks ago, maybe months ago. So if you want to do the evolutionary merging yourself, you can do it, and you should. Let me know if it works. And that's pretty much all I wanted to say today. So I'm going to thank my collaborators, and I'm here for any questions now.
Yeah, and like if you guys have any questions, please just drop it down. So I'll ask my own question. Okay.
Yeah,
Um, so like in your paper regarding the um, task singular vectors, right?
right.
Um, can we can the compression ratio be adaptive at as per the like what sort of task we do? So can we make it like adaptive per layer or per task based on the strength of the singular values, something like that?
Yeah, that's actually a smart idea, and it's so smart that people already did that. It's like it was one of the follow-ups we wanted to do, and somebody else was faster. So yeah, definitely on point on that. It's something that as maybe I don't know, a couple of months ago already was on archive, and it actually works well. So yeah, it's actually a nice idea, and
Oh,
you should do that. Like, I mean, here we don't have those experiments, but in that paper they say that it actually helps.
oh, that's nice to know.
Yeah,
Um,
definitely.
yeah. Okay. Also, okay. Let me just pull it up. Okay. Uh, so can we do it for other settings? Can we do task similar vectors for like other settings? Like, for example, let's say pruning or identifying redundant layers. Can we do something like that?
Yeah, that's actually a good idea. So okay, let me see. I was thinking about maybe using it for well, so we've got the compression use case, but I was also thinking if maybe it would be used together with quantization, and you can compress even more with that. Then pruning sounds like a good idea. Maybe you could try to use the entropy of the SVD, like the values of the singular values, and see if that tells you like maybe which layers you can drop. I mean, it sounds
Yeah,
reasonable actually. Yeah, I didn't try, but I think it's actually a good idea. I think it's something that should be looked into.
yeah,
And right now, I would even think that it might actually work. Actually, yeah.
yeah. Because I had this on top of my mind when you talked about this and like so I was just thinking because in pruning also we do sort of the same thing, right?
Hmm,
So
hmm.
yeah, that's why.
Yeah, I think that's a good idea. And I mean, if you if you try, do let me know, because I will be
Yeah,
curious, like if it actually works. Yeah.
yeah. Um, yeah. Do you guys have any questions? I think people don't have any questions. Are very shy, I think. Okay, yeah.
I mean,
Um,
it's also like before I clear, like we got a clear deadline on Thursday, so people are probably gonna be really tired now.
yeah,
Can
I
you?
totally relate. Yeah, I do hear you.
Okay. Maybe it's a stupid question, but is it possible to merge models that differ in size?
Yeah, okay. That's actually a good question, and it's something I've been trying to think about for a while now. Uh, the answer is yeah, to some degree, in the sense that if, for instance, the difference is just in the number of neurons that you have, so maybe let's say they have the same number of layers, but maybe the third layer in one network you got, I don't know, 10 neurons, and the other one you got 15, then you can still do something, and people do that with optimal transport. So basically, because instead of saying, okay, I'm going to match each neuron to each other one with optimal transport, you can say I'm going to give, I don't know, one half weight to this one neuron and one half weight to this other one neuron when matching this first neuron. So you can distribute the probability mass, like the weight, like the matching of one neuron to many different neurons. So if you do that, you can choose one of the two models as kind of your ambient model, and then map the other one with optimal transport to this one, and then you can take them in. So
Okay. Yeah.
in that case, you can. If instead you got different number of layers and so on, then it's another kind of problem, which is also really interesting, and it's something that I would like to do, but I only have 24 hours a day, which is front-end merging, which is this kind of crazy stuff people do a lot on Reddit and Hugging Face. They basically get, I don't know, Quen and Mistral and some other model, and they just add together, stitch layers together until they got some benefits. I remember there was one guy coming up with something like, I don't know, a 1 billion dimensional model made up of, I don't know, 7 billion smaller models. And it actually outperformed the comparable size other models or something like that. It was quite a crazy idea. But I have never tried. Like I know
Okay.
that they do something for in Sakana AI, in the paper from Sakana AI, they do something like that when they do the evolutionary stuff. Where was it? Yeah, in this one, oops, in this one year, they also try something which is close to Franklin emergent. I have to be honest, I don't remember. I mean, when I read the paper, it looked to me like it didn't make much more. Like it didn't actually justify the added weights and hovered. Like in the end, it didn't give much boost. So, but it's still another problem. Like I mean, there are so many things to try. This is the only paper I know of that actually tried to do something like that. Like other than that, it's just people trying stuff on Reddit and not publishing the paper. So I don't know what is
Yeah,
a reasonable way to do that.
yeah,
Okay. Thank you.
Sure.
yeah. We can just take one more question if people have. Also, somebody is asking for slides. If you can
Yeah,
share that.
definitely. Of course.
Okay, cool. Um, yeah. If there's no one more question, then yeah, we can end it. Yeah. Thank you, Donato. And this was actually very refreshing
Thank
topic,
you.
and yeah, I think everybody enjoyed it today. Yeah,
Thank you so much. Actually, had lots of
yeah,
fun, and I mean it's really nice to be here.
yeah, yeah. We hope to see you again. Yeah. Okay.
Yeah, definitely. All right.
Okay.
Thank you so
Chalo.
much, everyone.
Bye bye.
Enjoy. Bye bye.